Another example where you see this type of conflicting information is in an on-ball visual search task. Typically the way this task is described is something along the lines of, well, it's easier to find an oddball whenever it varies on 2 dimensions than when it varies on 1 dimension, because when it varies on 2 dimensions, it's more salient. And that's of course true. Here you have a case where only the length of the line varies, so this is somewhat more difficult. Here only orientation varies, that's also difficult. But when both of them vary, it's easier, and you're faster to respond whenever you have 2 things varying rather than 1 thing varying. I'm going to turn that on its head slightly and say that the reason why it's easier is because, in fact, whenever only 1 thing is varying, it shares information with the distractors which point you to the incorrect answer. So in fact, these 1 feature different, 1 feature similar cases are actually giving you conflicting information about the actual target. And there are a lot of theories of visual search which assume that you have some underlying initial salience map which is developed based on the local salience of those features, and this salience is then pooled into some sort of decision-making channel which drives your decision-making. Here's one example of that model where you've got an accumulator which accumulates the salience based on the length. Here's another accumulator based on the salience of the orientation. These provide you evidence which drives you to a threshold for detecting that target, and whenever you reach that threshold, you omit the target, and the time it takes you to get there determines the response time. A very common way of thinking about this type of oddball search is that, in fact, both of these differences are summed together and fed into a single decision-making channel. Now, if you remember from Mario's talk, each one of these models fall into a class of coactive processing models, because the information that you're getting from the stimulus is pooled together into a single decision-making channel. But that's not the only way in which you can process this type of conflicting information. So coactive models do provide one way of understanding the influence of conflicting information. The idea is that congruent targets are faster than incongruent or conflicting targets, because the conflicting information slows down the incongruent targets compared to the congruent targets. One important property that I'm going to explain in a moment is that the stronger the incongruent sources are, so the stronger that conflict, the more it slows you down in a coactive process. Another way, but this is only one way of thinking about how that information from each of those dimensions might be combined or integrated. As Mario pointed out, we can also talk about parallel processing models or serial processing models as well. And what I want to explore is how each of those architectures explain the effects of having different levels of conflicting information. To do that, I need to introduce the idea of capacity. In particular, I need to introduce the idea of minimum time processing. So I'll present you with a simple task that you can use to kind of think about these ideas. In this particular task, what your goal is to say yes anytime you detect the onset of a dot. The dot can appear either on the left or on the right, or it can appear in both locations, or it might not appear at all. If it doesn't appear at all, you have to respond no, nothing was detected. So parallel models, a particular type of parallel models, unlimited capacity, independent, parallel self-terminating models, predict that the time to process the double target should be equivalent to the minimum time that you derive from each of these 2 single targets. So I'm going to specify here that we have a double target. I'm going to call that A, B. And then we have 2 single targets, which I'm going to call A when it's on the left and B when it's on the right. And I can abuse mathematical notation here and just set up a simple kind of a relationship that the prediction from a parallel model is that the response time you expect from the double target should equal the minimum time that you derive from each of these 2 single targets on their own. Now, the appropriate mathematical notation, the way to express this relationship is in terms of the survivor functions. So this is the survivor function that we observe from the double target response time. That should be equivalent to the product of the survivor functions from the two single targets on their own under an unlimited capacity independent parallel self-terminating model. So Jim and his colleagues, Nazawa, used this property as a benchmark whenever they developed their measure of workload capacity. So here gives you some understanding about what the workload capacity function is attempting to capture. What we have here is a ratio now of the negative log of the survivor function from the double target over the negative log of the product of the survivor functions of the two single targets. So the negative logarithm of the survivor function converts these survivor functions into hazard functions, which gives us the very nice property that the parallel models, this type of unlimited capacity parallel model, predicts that this capacity function should equal 1 for all response time. So it gives us a flat function we can use as a benchmark when looking at the other models. Okay. What I want to do now is introduce some conflicting information. So rather than having nothing here, we're actually going to have two white dots. Here we'll have two black dots you have to detect. The task is the same. You still have to say yes anytime you see a black dot. But in fact, with the single targets now, they're no longer single targets because they're always going to be comprised of one white dot and one black dot. So you have one response that you make if you see two white dots, and another response you make if you see any black dots. But these stimuli now provide you with some conflicting information. On the one hand, there's a black dot there pushing you towards the correct answer. On the other hand, there's a white dot there, which is pushing you towards the incorrect node. So you've got conflicting information. Now for a parallel model, it doesn't matter whether we introduce some conflicting source into the other parallel channel. The minimum time that we predict from the two single targets previously should be equivalent to the minimum time we predict here. And the reason for that is because I've set up this assumption that the dimensions are in fact processed independently. And this conflicting information source doesn't allow you to make a correct decision. And I'm focusing here only on correct decisions. So if you want to predict this double target, the prediction is that from a parallel, independent, unlimited capacity, self-terminating model, you ought to still be able to predict that from the minimum time you derive from these two conflicting targets. So we're no longer dealing with workload because the workload in each of these cases is the same, but the congruency of the information sources varies. So here we've got a congruent redundant target where both of the sources of information are pointing you in the same direction, and here we've got cases where they're pointing in opposite directions. So for a parallel model, congruent targets should be faster than incongruent targets. This would occur solely due to statistical facilitation, so the minimum time property. But there's no effect of conflicting information sources. And this has been known in the literature. Gordon Logan used this to examine the flanker task and argued that in the flanker task, whenever you see this effect of the conflicting information, this falsifies what you would expect under an unlimited capacity parallel model. And he used this as a motivation for modifying Klaus-Bundeson's theory of visual attributes model, turning it into effectively a coactive model that was able to explain that particular data. Now, capacity in a serial model, serial self-terminating model, predicts that the time to process the double target should be slower than the minimum time that you derive from the two single targets. So if we, again, run this task and derive the minimum time from the two single targets, a serial model, because you process just one of these, so the response time. So the assumption here is you're processing these channels in a serial self-terminating fashion. So as soon as you detect either of these particular onset of these dots, you'll emit a response. Stop making a decision and emit a response. So the response time for the double target should just be the time it takes you to process one of these dots, which is equal to one of the single targets, but that's slower than the minimum time you derive from both. So we can add now, we look at the capacity measure. Serial models should predict that certain classes of serial models could predict that this capacity function is less than 1 for all response times. Coactive models, I haven't really told you about them, but they predict something called supercapacity, which is a capacity coefficient of greater than 1. Now, if we introduce our conflicting information sources and see what serial models do, they predict that the double target, this AB target, will be faster or slower than the minimum. So a serial model, so the minimum time, the minimum time of the single targets depends on the rate at which you can process both of these features. If, for instance, the distracting information can be quickly rejected, then the minimum time that you will derive from these two stimuli might be quite fast. Might in fact be faster than the time it takes you to process both of these targets if the time it takes you to process those happens to be slow. On the other hand, the distracting, conflicting information might slow you down a lot if you're trying to do this in a serial fashion, in which case the minimum time will be slow, the minimum time you derive from these two targets, meaning that it might be likely that this double target can be faster than. So the idea is that whether or not a serial model produces a double target response time which is faster or slower than the derived minimum time depends on the rate of processing of that conflicting source of information. So for coactive models, there's this relationship that the stronger the conflicting information, the more it slows you down. Weak conflicting information doesn't slow you down as much. You're pulling together now some information which points you to the correct answer and some information which points you to the incorrect answer. The stronger that information that points you to the incorrect answer, the slower your response gets. Parallel models don't predict any effective conflict strength. But for serial models, the prediction goes in the opposite direction. And the reason for this is because you're processing these things one at a time. If you have very strong evidence for the incorrect response, you can quickly reject it and move on to processing the correct response, the correct source of information. If you have weak evidence for the incorrect response, it takes you a lot longer to process it and move on. So we can in fact just modify the capacity coefficient function slightly by allowing now the single targets to have some conflicting information. I've indicated there by these subscripts, y and x, that I've put on these single targets. And I've given it a different letter just so we can tell them apart. I'm calling it resiliency, because I tried to call it capacity with distractor, but the viewer didn't like that. So the value of this particular function varies with the rate of processing of the conflicting information for all of the models except for the parallel self-terminating model. So to actually test this, what we need to do is use a task in which the redundant target, so this target here, the double target, is compared to conflicting targets, which have varying degrees of saliency of the conflicting information. And the task I'm going to tell you about is pretty much identical to the one Mario had just introduced. So here we have a particular target category where we have a factorial manipulation of information. I've labeled these, I've given them these labels here to indicate just how difficult it is to sort of reject each of these items or make a categorization decision compared to each of these boundaries. So this particular item has kind of low discriminability on both of the dimensions. So I've tagged it low, low. This one is easy because it has high discriminability on both dimensions. It's very far from both of these boundaries. I've tagged it high, high. For the contrast category, I've listed our double target here. And then we also have two conflicting targets on both dimensions. One of them has a conflicting bit of information which is very far from the boundary, so it's a strong, gives you very strong evidence for the target category, which is actually the incorrect answer in this case. And another one has very weak evidence for the target category. The level of the good information that you want to use is always the same because it's equally distant from that boundary across all three of these, certainly the same for these three here. So this incongruent source is hard to reject. It's weak evidence for the incorrect target category, but it's also gives you some evidence for the contrast category because it's quite close to that boundary. This particular conflicting source of information is easy to reject. It gives you very strong evidence for the incorrect target category. Under a serial process, it's very easy to reject this as being not providing you with the information you need to correctly make a contrast category decision. So what we can do is take the stimuli from this particular task, and what I've shown you here are the results of simulations for computing this RT function for both these low salience conflicts. So that would be the case whenever I compare this double target to these two double targets, to the case where I compare this double target to the two high salience targets. And what we can do is look at how those particular low and high salience target cases change as a function of the salience of the conflicting information for each of the models. So the first two models shown here are, so the red line here gives you the value of the RT function. The blue lines are bootstrap confidence intervals, but you can ignore those because they're just a function of how many simulation iterations are ran. They don't really tell us anything. The first two models, this serial model, this is a serial self-terminating model in which you always process one dimension before the other dimension. So it's a fixed order serial self-terminating model. This is a mixed order serial self-terminating model in which there is a 50% probability you process one dimension first, 50% probability you process the other dimension first. The key thing to note is that as we increase the salience of the conflicting information, the resiliency function actually decreases in magnitude. So it shifts down. So as the conflicting information becomes easier to dismiss, the derived minimum time becomes faster, making it less likely that the double target will exceed it, and thereby decreasing the resiliency function. So for a parallel model, it's the next model in line, there's no difference between these two functions because the conflicting information source doesn't actually do anything to the minimum time. So the rate of the conflicting information, the rate of processing of the conflicting information makes no difference, resulting in a resiliency of 1 across all t. For a coactive model, we see the opposite pattern. So as the conflicting information becomes stronger, the derived minimum time becomes slower, making it more likely that this double target will exceed it, and increasing the resiliency function as you move from the low salience case to the high salience case. For the parallel exhaustive model and the serial exhaustive model, we see similar patterns in that the low salience conflict slows down the incongruent targets more than the high salience conflict, meaning that the minimum time is slowed down more in the low salience case, making it more likely that the double target is going to exceed the derived minimum time, and pushing or making the resiliency function larger for the low salience case than the high salience case. So if we just went out and applied resiliency on its own, we wouldn't really be able to tell much about the underlying processing architecture. These curves on their own for just one of these cases don't really give us any clear signal about what the underlying processing architecture actually is. But as we vary the salience of the conflicting information, we get very clear patterns of the direction in which that resiliency function should move. So in fact, what we can do is just subtract these two functions and recover the identifiability of each of the architectures. So if we subtract now the low salience resiliency function from the high salience resiliency function, the serial model, serial self-terminating model, and the exhaustive models predict that we ought to see a resiliency function which is less than 0. The parallel model predicts that we should see a resiliency function which equals 0, and a coactive model predicts a resiliency function which is greater than 0. If we make some assumptions about the ordering of these distributions, the ordering of the conflicting information, and the invariance of the congruent information, then we can actually prove that these relationships hold. So this is sort of a novel measure of information processing that has to do with whenever you've got conflicting information sources. So let me show you some evidence that this actually works. So this is some work that was conducted with Mario and Rob Lazovsky, along with some others, where we use the SIC now, based on the target category responses, to compute some sort of index of what the underlying architecture was. And what I'm going to do is I'm going to show you that data, and then I'm going to compare that to the predictions that we get out of this resiliency difference function. So just to remind you, these are the types of predictions that we'll be looking at from this particular task. So because a member of this target category has to be both greater than this horizontal boundary and greater than this boundary, we can concern ourselves only with the exhausted SIC predictions. So we get an S-shaped function like this. That's evidence of serial exhaustive processing. A completely negative function would be evidence of a parallel exhaustive process. And this sort of mostly positive function with a little initial negative blip would be evidence of a coactive process. And we compute the SIC by taking the sum of the differences between the survivor functions for those particular items that Mario explained. Okay, so in this particular experiment, each one of these stimuli were shown to people one at a time, and they had to make a categorization response. In some cases, we told people, hey, we want you to look at the base of this lamp first, so the base is one dimension, and then we want you to look at the top of the lamp. So the top is the other dimension. There's a lot of other stuff varying here, but you can ignore that. In other cases, we didn't tell them what to do at all, we just let them learn. The results turned out the same either way. We found SIC signatures, which look like very clear serial exhaustive processing for the target category. We had independent modeling evidence and also evidence from these particular data here that showed us that in fact they were processing these items in a serial self-terminating fashion. This was serial exhaustive solely due to the nature of the task. Our best guess at what people were actually doing was processing one of these dimensions and then stopping if they could terminate their decision after that particular dimension. We compute the resiliency difference function. We see that it's less than 0 across all of the response times, which is consistent with what I just told you about what we expect from a serial self-terminated model. Here's data where now we didn't tell them what we wanted them to do. We just let them learn these stimuli over time. Again, we saw very clear serial processing in the SIC, or very clear evidence of additivity. And again, the resiliency difference function is less than 0. Here's a case where we use integral dimension stimuli. So these are Munsell colors varying on their saturation and their brightness. Here, our best guess at what the underlying SIC was telling us was that, in fact, processing was coactive. So both saturation and brightness were being pooled into a single processing channel. Now when we compute the resiliency difference function, it's greater than 0, consistent with the idea that whenever you've got conflicting information, the stronger the conflicting information source, the slower the coactive process. Here's a case where now we've got separable dimension stimuli, but the dimensions are not located in different spatial locations. So if I show you these lamps, these are actually pretty big on the screen. They're probably 15 degrees of visual angle separation. So in fact, you could fixate on one dimension and then shift your point of fixation to another dimension. So it's perhaps not surprising that we found serial processing. For these stimuli, though, both of the features now, the saturation of the background of the stimulus and the position of this inset vertical line are in the same location. Here we find the processing sometimes looks serial and other times looks parallel. Using some parametric models, which I'll talk more about tomorrow, our best guess at what people were doing was something like a mixture, a trial-by-trial mixture of serial and parallel processing. Sometimes they process the dimensions in serial, sometimes they process them in parallel. This is following on from one of the questions that came after the last talk. The resiliency difference function in this particular case is less than 0, consistent with some serial processing for the contrast category items, even in the case when the SIC signature looks mostly parallel. So those were 4 examples where we had independent evidence about what the underlying processing architecture was based on the SIC. We can also do tasks like the Simon task, where now we don't have any independent evidence, but we've got some theoretical suggestions that processing should in fact be coactive. And whenever we compute the resiliency across the number of observers who completed the Simon task, most of the time it's greater than 0, as you'd expect from the theoretical model that I presented earlier. We did the same thing for the flanker task, and again found that the resiliency difference tended to be greater than 0, supporting the idea that there's some coactive integration of the target information and the distractor information. So, in the latter two situations, we didn't use the full power of the systems factorial technology, but just using the original task design, we could go in and apply this new measure and tease out something about the information processing architecture, particularly how it processes this conflicting information. So this resiliency difference function quantifies the relationship between congruent and incongruent targets in the same sort of non-parametric fashion that the other systems factorial technology measures do, so the SICs and the workload capacity measure. It explains why and how different models predict the cost for conflicting information. And it provides convergent evidence to other non-parametric measures. And it extends the domain of the systems factorial technology to conflicting information sources. It's limited in that it only currently deals with correct responses, but as I suggested, whenever you have this sort of conflict, it's likely to lead to an increase in errors as well. Certainly for the categorization tasks, accuracy was pretty high. We didn't have a lot of errors, so we could get away with applying this information, or this measure. Also in the flanker task and Simon task, we didn't have a lot of errors either, but you could expect that under a lot of more realistic situations, when you have conflicting information, you're going to make mistakes. In which case, one point of development that needs to happen is we need to extend this type of theory to deal with accuracy and not just response time. It's also currently limited to models exhibiting channel independence, and a lot of work coming out of Jim's lab, a lot of work done by Joe and Amit, has looked at whenever you have cross-channel dependencies in parallel models. The same sort of work needs to be applied here as well. And finally, just to give you a kind of another way of thinking about this, one of the things that came out of the work with Mario and Rob Mazovsky was that each one of these models makes unique predictions for the mean RTs from that contrast category. So here you've got your double target. Here is your low salience conflicting target. Here's your high salience conflicting target. And you see a very neat relationship here. So this is something which was noted just falling out of the simulations of these models. If you have a parallel self-terminating model, well, there's no effect of this conflicting information. If you have a coactive model, then you get an increase in the mean response time as the conflicting information source increases. But for a serial self-terminating model, it either stays the same if you've got a fixed order on one dimension, but it decreases on the other dimension, or if you've got a mixed order serial self-terminating process, it decreases on both dimensions. And I'm not going to take you through all of this, but there's actually a very easy way to see this relationship. Well, I'll take you through some of it. I'll put it up here. If we take the capacity coefficient function and actually invert it, so now what we've got is something like the inverse capacity function, where you've now got the two single targets on top of the equation and the two double targets on the bottom. Then, and we compute the difference between the high salience one and the low salience one, the conflicting information sources. Then you can simplify this so you get a nice sum of the differences between the high salience and the low salience case. I think I'll remove all the math there. So you've got a difference between the high salience conflicting source and the low salience conflicting source on one dimension, added to the same difference on the other dimension. So you just take a sum of the differences. Now, Jim showed in a paper in 1990 that if the hazard functions are ordered, then the means of those functions are also ordered. So, in effect, if this relationship is true, then we can simplify that and look at something I'm calling the mean conflict contrast function. where you just can look at a simple difference between the means to get some idea about the directionality of things. And that maps back to these predictions that we saw falling out of the parametric versions of these models. So one final thing that I think this work kind of suggests is that whenever you've got this type of conflicting information or this distracting information, and you're computing a measure which is based on the minimum time, so something like capacity or something like the race model inequality. So the idea behind the race model inequality task is, this is an experiment reported by Mordkov and Yantis in '93. The idea was you had to respond yes anytime you saw an X or anytime you saw the color green. So again, you had two single targets. So this is an X on its own, this is green on its own. This is a double target, green X. We also had some non-targets. So these single targets are not pure single targets. They carry information about the non-targets. So this is also not an X. So it falls into this non-target category. This is also not green. So if you want to compute the race model inequality, you need to take into account the idea that whenever you've got this conflicting information, that derived minimum time can actually slow down. So any of those models, depending on the rate of processing of that distracting information, might be able to violate the race model inequality. And I think Jim used similar ideas to this to show that a serial exhaustive model could in fact violate the race model inequality. I'll leave you with that, and we can all go to lunch. If you have any questions, I'd be happy to answer it. Thanks very much. In the experiments that we've looked at, accuracy has not been a problem. I'm just proposing it as something that is a tough issue to tackle. One of the reasons for that is because if you think about a single channel model, there are a lot of different theories for how errors and error response time arise. So you've got, something like a diffusion model where you've got two boundaries. You're correct if you hit one boundary, you're incorrect if you hit the other boundary. As you start developing more complicated architectures, the way in which these errors can arise becomes a lot more complicated. So you could have a failure of one component of the architecture that doesn't lead to an error because the other component of the architecture still succeeds. Or you could have both components fail and end up at the correct answer. So there's a lot of complicated, the error response times end up being a probabilistic mixture of a lot of these different ways in which the components of these models can actually fail. So deriving the predictions for them is somewhat more complicated. So a bit of work that I see has to happen, but in the case where you've got highly accurate responding, like in the experiments I described, you probably go right about thinking about it.
Just how would you go about, I guess your way, but your perspective on, you've got basically you're studying anti-configuration here. It's another way of saying with the anti and the pro, so to speak, you have general context effects, which again, tend to develop essence to part of the study. How would you go about, say, doing a study where you, in some way, some of the design here might give you superiority of the double target simply because the conflict is worse, is a lot worse than your single target. So how would you see your study so that you can see both configural superiority as well as configural inferiority and yet teach them all out at the same time?
Great question. I'm not sure I know the answer. I think you'd have to first determine whether configural superiority is arising actually due to a configural processing. So I totally agree with Mario that the way of defining configural processing is probably something like coactivity. But you can also have things which look like configural superiority, which arise for reasons that don't have to do with coactivity. Have to do with other types of architectures. Yeah, so I'm not sure exactly I have got a good answer to how you would design an experiment to look at those sorts of things. I think it would depend a lot on the types of stimuli you're interested in, the kinds of things you want to do with them. Yeah.
Okay, well, that's your homework. No, just kidding.